So as Claire said, I'm Dr. Stephen Wilkins. Just to give you a bit of a wider background, I was born in Leeds, as you can maybe tell from the slight northern twang that I still have. It's been southernified by many years of being exiled to the south though. I did my undergraduate education at the University of Durham, so I decided to go a little bit further north in my first step. Deciding that I didn't like the north anymore, I decided to move down to the University of Cambridge for my PhD. Deciding that that was about the right latitude for me, I decided to move over to Oxford afterwards and go to the other place. And then I decided what I really wanted was to live by the sea, so I moved to the University of Sussex, where I became a lecturer in 2013. And as of a month ago, I was promoted to reader in physics and astronomy. At Sussex, I'm also very active in public engagement, so I'm a public engagement fellow, which means that I'm paid by my research council to actually do things like this. But on a day-to-day basis, I give lots of talks to schools and to other audiences. As part of my public engagement fellowship, I have recently also established a science education charity in Sussex. The idea of this charity is really to engage mostly young families with science from a relatively young age. So I'm talking about primary school level children over here. And so we're only just starting now, but we've had our first successful events now, reaching several thousand people on a couple of one-day events. And so I hope to do that in the future. My actual research is a little bit disconnected from the theme of today's talk. So my actual research focuses on exploring the very early universe, so the formation of the first stars and galaxies. This is something which is accessible because the speed of light is finite, and that means it takes light a certain amount of time to travel across the universe and reach us. So as I look out into the audience today, I see you as you actually appeared a fraction of a second ago. Now, with modern observatories like the Hubble Space Telescope, which I've used frequently throughout my career, we're now able to look back almost over the entire history of the universe. What I'm really working on at the moment, I'm very, very passionate about, and the source of actually most of my public engagement activities, is this new telescope that we're currently constructing at the moment. This is the Webb Telescope, which will hopefully be launched in 2021. Now, anybody who's familiar with this project will understand why I said hopefully. This is a project which should have actually been launched around 10 years ago and has been successively delayed. But the hope is that it's on progress now. And so, if you look over here, we can actually see a picture of the telescope going in for testing now almost a year ago. In terms of this talk, though, I decided I want to celebrate the 150th anniversary of the periodic table. I'm actually not going to talk a lot about the history of the periodic table. I'm just going to use this as a stepping stone. So the periodic table was very important because it was one of the first attempts for us to understand the structures of atoms. So actually, by making this table, the original scientist involved, most prominently Dmitri Mendeleev, actually allowed us to ultimately work out why atoms have different properties, how they're different from each other. And so this was a really first step in the formulation of understanding the elements. In today's talk, what I'm going to do is split it into 3 parts. So in the first part, I'm going to give you an introduction to effectively nuclear physics. This is something that you might not have seen for several years, but I'll try and go through it as simply as possible. And then I'll talk about, well, what elements actually exist in the universe, and are they the same everywhere? So I'll talk about the abundance of elements in our solar system, in the Earth, and actually in our bodies. And then the bulk of the talk will be astronomy. So the bulk of the talk will focus on how these elements were actually made, from the ones in our bodies to maybe the gold on your ring. Okay. So jumping straight in with atoms. So I'm now going to talk about what atoms are and how they're rearranged by nature. So every atom is composed of a nucleus. This contains 1 or more protons, and a similar number of neutrons as well. Collectively, the protons and neutrons are the nucleons, and they form the nucleus. Actually, about 99.99% of the mass is actually in the nucleus. So only a relatively small fraction of the mass is contained in the electrons which orbit the nucleus. And so we have this kind of, what actually turns out to be a fairly naive picture, but where we have protons and neutrons contained in a nucleus surrounded by a cloud of electrons. Any 2 atoms with identical number of protons are the same periodic element. Okay? But at the same time, an atom can have different number of neutrons. So these are the isotopes. So we have chemical elements which can have multiple different isotopes. So for example, looking at the simplest element, we have hydrogen. The hydrogen that most people are familiar with and actually makes up most of the hydrogen that's in water is actually hydrogen 1. This just contains a single proton in its nucleus. But there are also important isotopes like deuterium and tritium. Tritium over here has this little symbol next to it because it's actually unstable and it will decay given long enough. And then helium as well, it has two common stable isotopes, helium-3 and helium-4. Now, isotopes have very similar chemical and molecular properties, but they actually have different masses because of the different number of neutrons, but really crucially, they have different stabilities. Okay. So what I'm now going to talk about is how you can actually rearrange atoms to make new elements. So I'm going to start off with what turns out to actually be the most important process, and that's nuclear fusion. In nuclear fusion, this is a reaction where you combine two atomic nuclei together to form a new nuclei. And in many cases, this actually produces energy as well. To fuse atomic nuclei, though, it's very, very difficult, and you actually have to overcome the repulsive force of the two nuclei. So both the nuclei are positively charged, they don't like being together. And so in order to actually fuse anything, you need to get these two nuclei very close together. That only really happens at very, very high temperatures and densities. Okay? And so, for example, this is just one nuclear reaction that I'm demonstrating over here. This nuclear reaction isn't actually very important in astrophysics because there isn't a lot of tritium and deuterium in stars, but this is the nuclear reaction that we one day hope to actually exploit on the Earth to give us an almost limitless supply of clean energy. Okay, and so what happens in this reaction is that we have tritium and deuterium fusing together. Okay, so they come together. This is very, very difficult, this initial stage, but once they're close enough, a different force of nature, the strong nuclear force, takes over and they're able to merge together. And in this case, deuterium and tritium are fused together to produce energy, but also helium-4. So we've taken hydrogen and helium, and we've combined them together to form a new type of helium in this case. But really crucially, this reaction produces energy, and this is the reason why we want to harness this reaction on the Earth. It turns out the reason why I show this reaction is because it's one of the easiest reactions. It requires one of the lowest temperatures to actually undertake. There are other ways of actually rearranging and making new atoms as well. A really, really important one is called neutron capture. This is kind of similar to fusion, but all that's really involved here is that an atom, in this case silver 109, captures a single neutron and becomes silver 110. Okay? So by capturing a neutron, what you're going to do is create a new isotope of the same element. Okay? But in this case, we can see that actually the silver 110 is unstable. So it wants to break apart to form something new. And I'll come back to this in a second because this is really crucial for creating all the very heavy elements, including the gold on your jewelry. So there are ways that atoms can also break apart. So we've talked about building them up from small building blocks together. This is nuclear fusion and neutron capture, but there are also ways they can break apart. So there's three reactions here which you might be familiar with. So first of all, there's alpha decay, where an atom will just essentially lose a helium nucleus to become a lower mass atom. There is beta decay. This is the really important one. For example, silver 110 can convert one of its neutrons into a proton, an electron, and an antineutrino. What this means is that silver 110 can transmute to form a new element, cadmium 110. In this case, the cadmium is actually stable, whereas the silver 110 wasn't stable. And it's actually this process here which is really, really crucial for explaining many of the very heavy elements. Okay. We also have spontaneous fission, which is really important in commercial nuclear reactors that we use today. So around 20% of our energy needs in this country are created via reactions like this, where an unstable nucleus, for example in this case uranium-236, breaks apart to form two lower mass nuclei. Okay. So that was my little primer on nuclear physics. What I'm going to do now is talk about the abundances of elements in the universe, including both the solar system, the Earth's crust, and our own bodies. So if I just very naively make a pie chart of all of the elements in the universe, weighted by their mass, I get something which looks a little bit boring like this. So it turns out that most of the mass of the universe is actually in hydrogen. So this is around 75% of the mass of the universe, at least in normal matter. I'll come back to that distinction later. At least in normal matter is in hydrogen. okay, with around 23% in helium, and then all of the rest is only this 2%, and this contains all of the other heavy elements. So this diagram, as I showed you here, isn't particularly informative. We can't really see how much of a contribution all of the heavier elements, including even oxygen, really make to the universe. So what I'm going to do is, instead of using a pie chart like that, I'm going to rely on actually color-coding the entire periodic table, the form that you might be familiar with. I'm going to color-code it by the abundance in the solar system. But I'm going to use a very special color coding here. I'm going to use a logarithmic scale. So all we really need to worry about this is that if we're yellow over here, that means we're very abundant. Okay, so hydrogen will be up here in the universe because it's very abundant, whereas things which are very rare, like gold, and we can see this is the fractional abundance, will be down here in the deep blues. Okay, so I'm going to use this color scale to color code my periodic table now. And so when I do this for the elements in the solar system, this is the result. So we can see straight away that hydrogen and helium, being the most abundant elements in the universe, have these very bright yellow colors corresponding over here. But what we can see is, in general, as we move down the periodic table to heavier and heavier elements, the elements become rarer and rarer. Okay? There are some exceptions to this, like beryllium and boron over here. They're actually relatively rare, despite the fact they're very low mass. But we see that now we get to see the contrast between the other elements. So the next most abundant elements are things like carbon, nitrogen, and oxygen. But then we also see iron and nickel becoming very prominent here. So you can see that there are some elements missing on this diagram, some elements that aren't colored at all. That's because they're either unstable, and so they exist in minute quantities at any one time. Okay, so abundance is well below here, or that we don't actually have a good idea of their abundance because it is so low. So for example, technetium over here doesn't have any stable isotopes. Every single isotope wants to decay to something else. Okay, so it only exists as a very transitory element. Okay, but we can see things like the gold and the silver and the platinum over here. These are all very rare compared to other elements in the universe. Okay. Again, here I'm using the solar system as a proxy for the universe. The reason why I'm doing that is because it's very difficult to actually do this same measurement for the entire universe. The reason for that is, as we look out into the universe, as I mentioned earlier, we're actually looking back in time. And we expect this pattern of abundances to not only change on your position in the universe, but also with time. Okay? And this is something that I'll come back to later as I discuss the origins of all the elements. So let's now look at the Earth's crust. Again, I'll show you the familiar pie chart. This looks very different now. So gone is the hydrogen, gone is the helium. In fact, there is still some hydrogen, it's down here in this little slice, but it's really dominated by things like oxygen and silicon now, and iron, aluminium, magnesium, and sodium. Okay? But still, the elements that maybe we care about, all the gold is down here. I actually forgot to explain this. I missed something crucial from the very beginning of my talk, why I was going to keep talking about gold, and I'm going to go back and explain this, because it is really important to me. So the telescope that I work on, the Webb Telescope, which is under construction right now, looks like this. It looks gold here because it is gold. The Webb Telescope is coated in a very thin layer of gold. The reason for this is that gold actually reflects infrared light, which the Webb Telescope will observe, much more efficiently than silver or aluminium, which our normal telescopes are made out of. So this is one of the reasons why I really care about gold, because it is crucial to the science that I want to do. So while I'm flicking through, I'm just going to have a drink. Had I realised this was such a slow clicker, I probably wouldn't have done that. That's right.
For beta decay, it's just lost a neutron, so the silver and cadmium should have the same number of protons.
So the neutron is actually converted into a proton and an electron. So effectively that's what happens. That's what it looks like from the outside. It's a little bit more subtle than that. Okay, so I was back here. So this is the pie chart of the Earth's crust, and again, you can now see a very different distribution compared to the solar system at large. Now, the two elements that are really crucially missing from here are hydrogen and helium. Okay, there is actually some hydrogen here and a tiny, tiny fraction of helium. And that's because those elements actually want to escape the Earth's atmosphere and can escape the Earth's crust relatively easy. And so if we go back to our periodic table, we now see a very different pattern. So gone is the helium, okay, but new elements now becoming more prominent. So in particular, the oxygen, the silicon, the iron, okay. Interesting to note that in the Earth's crust, the abundance of helium is not far off the abundance of gold or silver. All right. And this is despite helium being the second most abundant element in the universe. In the Earth's crust, it's relatively rare. Okay, but what about humans? Again, I'm kind of moving the different levels here from the solar system to the Earth's crust and now looking at humans. Now, when we look at humans, we see a different picture again, okay, showing the pie chart over here. But again, I'm just going to switch straight to my periodic table and show you this. Again, we now see a completely different pattern of elements. The noble gases are all gone, okay, and we see that oxygen and carbon take on new responsibilities here. This is a little bit deceptive because not all of these elements have a biological role in our bodies. And so what I'm going to do is actually just take the ones that don't have a biological role and just fade them out for a second. All of these elements here do play a biological role in our body, with the exception of the ones with question marks, whereas it's not actually confirmed yet whether they do play a biological role. But several of these elements are particularly rare, like the cobalt and the molybdenum. As I understand, these both play a role in certain enzymes, which are really crucial for actually using oxygen inside our bodies. Okay. So what I want to do now is to try and explain the origin of all of these elements. Okay. As it turns out, the origin of virtually every element, apart from the ones that we've made in labs, is astrophysical in origin. And it's a whole variety of different processes. We're going to work our way to a final process, which was only actually confirmed 2 years ago and actually helps explain many of the most massive elements. So to do this, I'm going to rely on my periodic table diagram again. I'm going to use the solar system version because this is the most representative. And what I'm going to do is I'm going to take us through several different processes which produce the different elements. And the way that I'm going to use this diagram over here is to, in addition to color coding by the abundance, I'm also going to use the opacity or the transparency to give an idea of how much of that element we've accounted for so far. Okay? So for example, if I've accounted for all of a very rare element, it will be colored somewhere up here. If I've only accounted for half of a very rare element, it will be somewhere down here. Okay? And conversely, if I've accounted for something which is very abundant, it will be over here. Again, it'll be much more obvious as we go through to see this in practice. The first process I'm going to talk about was really the first nuclear process which occurred in the universe's history. The current consensus in cosmology and astronomy is that our universe is expanding. A consequence of this expansion is that as we go back in time, the universe will get hotter and denser. If we extrapolate all the way back to the very early universe, to the first few seconds of the universe's history, the universe should be so hot and so dense that atomic nuclei shouldn't be able to exist. If they ever formed, they would be immediately broken apart because the universe is so energetic. Okay, so you could form atomic nuclei, but they would very, very quickly get broken apart. Okay, so for the first 10 seconds of the universe's history, there was no chemistry. Okay, there was essentially just free particles in the universe. If we go back even further, even some of what we consider fundamental particles actually get broken apart into their constituents. But what happens next? Well, as the universe expanded, after about 10 seconds, the universe cooled enough that we could start undergoing nuclear fusion. So the point here is that we could make elements via nuclear fusion and they weren't immediately destroyed. Okay? And so in the early universe, we started off with the protons and neutrons. These can combine to form deuterium. The deuterium can then combine with another proton to form helium-3, and so on and so on and so on, making all the way up to helium-4 over here. So in the very early universe, in fact, in the first roughly 10 or 20 minutes of the universe's history, what happened was the protons and the neutrons which existed were converted into helium-4. Now, it turns out that neutrons were significantly rarer than protons in the early universe. So what happens is that all of the neutrons get converted into helium, but not all of the protons. And so we go from something like this. So the blue ones here are the protons, the purple are the neutrons, and we convert these into this. So around 20 minutes later, the universe has converted all of the neutrons here into helium, and then all of the protons are just left over, forming hydrogen 1. Okay. This process just about stops here, and I'll explain why you don't really go much beyond helium in a second. But it turns out you can create a very small amount of lithium during this process as well, but it's almost negligible compared to the amount of hydrogen and helium. And so if we go to our periodic table now, this is the somewhat depressing picture that we're faced with. So just based on this first 10 or 20 minutes of the universe's history, all we've done is explain the hydrogen and most, but not all of the helium, and a tiny sliver of the lithium over here, which is already very rare. The rest of the periodic table is still open and hasn't yet been populated. So in the first 10 or 20 minutes of the universe's history, all we've really made is what we call primordial chemistry, or primordial elements over here. So what happens next? Well, as the universe expands, it continues to cool. At some point, the gas which is in the universe can start to collapse under its own gravity. And in very localized areas, you can collapse gas to form stars. So stars forming structures like this. This is one of my favorite pictures from Hubble. This is the Pillars of Creation, which is actually a portion of the Eagle Nebula. What's going on here is these are thick clouds of gas and dust. It's actually the dust that makes them look black or very dark colors. But inside these clouds, you actually have stars that are forming from this gas. So what happens in star formation is that we take a cloud of gas, it collapses under gravity. Gravity is winning. But at some point, the temperature in the middle of the cloud of gas becomes high enough that you can actually trigger nuclear fusion. And that produces energy. That energy provides a source of pressure which stops that gas cloud, which is now a star, collapsing further, at least for a period of time. And so this is really our definition of a star over here, something which is fusing hydrogen in its core to produce a source of energy which stops it collapsing under gravity. And so when we look a little bit later, this is what we see. So this is a relatively young cluster of stars, which is formed from some of this material over here. Okay, so we see that stars preferentially form in clusters containing between hundreds and hundreds of millions of stars in a go. Now, for most of a star's lifetime, what it does is just fuse hydrogen, so the leftover protons from the early universe, to produce helium. Now, at the time, this produces energy as well. So for around 95% of a star's lifetime, this is what it's doing. This is what the sun is doing right now. In the sun's core, it's fusing hydrogen to produce helium. That produces energy. That energy stops the star and the sun from collapsing, but ultimately some of that energy gets out, and this is what lights up the Earth today. Now, eventually, a star will run out of hydrogen in its core. It will exhaust the hydrogen that it has available to it. Now, unfortunately, fusing helium is very tricky, and not all stars are able to make this next step. So stars about half the mass of the sun and below never actually go beyond fusing hydrogen to helium. They just stop there. But stars like the sun can fuse beyond helium. But it's actually really tricky. And the reason why it's really tricky, and this is the reason why it doesn't really occur in the very early universe, is that when you fuse two helium nuclei together, you form beryllium, or beryllium-8 specifically. Now, this isotope of beryllium is actually unstable, and it wants to decay back to the helium nuclei. So the only way we can actually fuse beyond helium is to very rapidly fuse this beryllium with something else before it decays. And so this is the triple alpha process. So what happens here is that we take 4 helium nuclei and we very rapidly fuse them together to form carbon-12, which is stable. So this is only a number of stars can do this. Only stars around half the mass of the sun and above can ever do this process. This process occurs after what we call the main sequence. So a star spends most of its lifetime holding itself up via fusion of hydrogen. When that hydrogen runs out, you will trigger helium fusion in some stars, including the Sun. Now, when this happens, it turns out the luminosity of that star will rapidly increase. Now, this causes the star to actually expand hugely, and you become something called a red giant. And so this is a very famous red giant over here. This is the star Betelgeuse, which is possibly more familiar as the top left-hand corner of the constellation of Orion over here, which we could almost certainly see tonight if it's not below the skyline. Okay, so this is a red giant star. This is a star which has stopped fusing hydrogen in its core and is now powered by helium fusion. Now, stars like the Sun unfortunately never fuse beyond carbon and nitrogen. And the reason for that is, again, because carbon and nitrogen are now relatively big atoms. They're very, very difficult to get to merge together. You need to overcome this really strong repulsive force of the charges. Instead, in low-mass stars like the Sun, you end up with an inert lump of material called a white dwarf, combined with the loss of the outer layers of the star, which become a planetary nebulae. So we go from something like this, a low-mass main sequence star, we form a red giant, okay, if it's able to fuse helium, and then we form a planetary nebulae and a white dwarf. So let's look at what white dwarfs look like. This is not the white dwarf, this is the star Sirius A, the brightest star in the sky. Over here, Sirius A has a little companion called Sirius B. This is incredibly faint compared to Sirius A, but it is one of these white dwarfs. This is essentially a lump of inert carbon, nitrogen, oxygen, which is no longer undergoing nuclear fusion. The reason why it shines at all is that it has some internal energy still. It's just cooling over time, though. But I think most importantly, what happens during this stage is the star's outer layers get expelled, and they produce objects like this. These are planetary nebulae, and these are some of the most beautiful objects that astronomers have found. Okay? Every single one looks different, in each case betraying something about the star that formed it. In many cases, you see evidence for rotation in the star before this phase happened, for example, this one over here. But you also see that we have wonderfully complex ones, like this one over here, and then we have deceptively simple ones, like this little, almost like a soap bubble in space. Okay, so we see this huge diversity. Many of these are actually relatively accessible even with a small telescope. You can actually go out and see some of these. If anybody's curious about the name, the reason why they have this name Planetary Nebulae, it's nothing to do with planets. It's because when early astronomers looked at them through early telescopes, they saw that they had some extent on the sky. So they weren't just point sources like stars. So early astronomers thought they were maybe planets that are just really far away, which is why they don't move, like with respect to the stars. Okay. But unfortunately, that name has stuck with us through the intervening decades. So what do these low-mass stars, what do stars like the Sun do to our periodic table? Well, in fact, their contribution isn't huge. It turns out what they do is provide most of the remaining lithium and then a significant fraction of the carbon and nitrogen. This is actually a little bit deceptive because it turns out they do something down here, but they are only able to do anything down here if heavy elements already exist in their atmospheres. So you need to have some heavy elements for low-mass stars to actually make a contribution to other heavy elements. So I'll come back to this later. What about high-mass stars? Well, stars more massive than the Sun, or more massive than a few times the mass of the Sun, are able to actually fuse beyond helium and beyond the carbon, nitrogen, and oxygen. And they do this via a process called the alpha process or ladder. So what happens here is we, for example, take carbon-12, the product of the triple alpha process, and we combine it with another helium nucleus to form oxygen. And we can keep going in this reaction like this, building up successively more and more massive elements. Okay? So there's a bit of a gap here, and we work our way up to iron and nickel. Now this becomes important over here because all of these reactions here, as you fuse together the atoms, they actually produce energy. But this changes after iron and nickel. If you fuse beyond iron and nickel, you actually need to put more energy in than you'll get out. Now this is a real problem because it's only this process of fusion which is holding the star up in the first place. But a star doesn't know to stop. A star has some internal energy, it's very hot, and so it will get to iron and nickel and it will want to keep going. It will fuse beyond. But what will happen is you will sap the core of the star of all of its energy. And what that means is the star no longer has any way of supporting itself, and it dramatically collapses. Okay, so this is just a restatement of this. If we try and go beyond nickel and iron, the process becomes endothermic. It requires energy, and this saps the star's core of energy. So this is something called a core collapse supernovae. So the entire core of the star very quickly collapses into its own gravity, and this liberates a huge amount of energy that then rip the star apart. Now, really crucially, these supernovae disperse all of these products of fusion into space. And so when we look at these objects, they look something like this. So this is a supernova remnant. It looks very similar to a planetary nebulae. It is a very similar idea, but this is now driven by an exploding star. So let's look at the contribution of these stars to the periodic table. And now we're filling in loads and loads of the gaps. We see that we've really explained the oxygen, the really crucial one certainly here on the Earth and in our bodies, but also many of these other elements as well. We're also starting to populate the iron group of elements over here. Okay? But we can see that these are quite faint, and so there's still something missing. And we haven't really mentioned what's going on down here yet. Okay? But we've talked about low mass stars and we've talked about high mass stars. So what else is there? Well, this would be the case if all stars lived alone. But actually we know that stars don't live alone. In fact, the vast majority of stars in the universe live with other stars. They're gravitationally bound to other stars in binary or triple systems, or even higher order systems. Now, in some fraction of those cases, the stars can be so close together that they can actually interact with each other, and they can transfer material from one star to another star. So this is an artist's impression, unfortunately, but this is an example of this situation. So here we have a white dwarf, and it's stealing or accreting material from one of its very large diffuse neighbours. And so this is what we expect to happen. This white dwarf, because it's very, very dense and has very strong gravity, is able to pull some of the material off its neighbour. Now, this white dwarf is able to exist because there's a physical process which stops it from collapsing under its own gravity. But that physical process only lasts a certain way. This number that was developed for how big an object could be held up by this physical process was actually very famously developed by the scientist Chandrasekhar on a crossing from India to the UK in the 1930s. He wrote down the equations which actually gave us what this mass is. And it turns out if you make a white dwarf more massive than around 1.5 times the mass of the Sun, it will just collapse and it will explode. And that's what happens in these situations. We have a white dwarf steals material from its neighbour and it becomes too big to hold itself up. And it very rapidly collapses and it triggers a huge thermonuclear explosion. In a very short period of time, all of that carbon, nitrogen and oxygen gets fused to heavier elements all the way up to iron. You rip apart the star in a very, very rapid manner. These explosions are so luminous that a single explosion, a single star exploding over here, can outshine almost an entire galaxy. So this is a supernova explosion in this galaxy. This galaxy over here contains 100 billion stars thereabout. So this thing over here is comparable in brightness to this entire galaxy, and this is just one relatively small star exploding all in one go. But crucially, as it explodes, it's exploding because nuclear fusion is happening all over the star almost in one go. Again, like the core collapse supernovae in the Planetary Nebulae, it leaves a remnant behind, and this remnant is enriched with all of these heavy elements that were produced in this explosion. And so if we look what happens now, we can see that when we add in the exploding white dwarfs, we're almost able to explain the entire upper half of our periodic table, so virtually all of the light elements are now explained. Okay? Although you can see there are a couple of gaps that I'll come back to. Let's just see this in contrast. So I'm going to remove the white dwarfs now. Okay? So I've now removed the white dwarfs, and you can see that the main contribution that the white dwarfs are actually making is producing things like the iron over here. And again, this is a really crucial element for our own bodies in hemoglobin, but also crucially makes up a significant fraction of the mass of the Earth. But we can see there are gaps. And in particular, what I haven't really discussed yet is this gap over here. So the heavy elements down here. So how do they get formed? Well, if we remember all the way back to the beginning, there was this idea that I mentioned called neutron capture. Now, many of the nuclear reactions which are undergoing in the sun and other stars produce lots of free neutrons, lots of neutrons that can escape and can be captured by other elements. Okay? So these can be absorbed by nuclei to make successively heavier atoms. So let's see how this might happen. If we have silver over here, we know that if silver captures a neutron, it can become silver 110. But silver 110 is radioactive, and it wants to decay via the beta decay. Now, what the beta decay does is move us up in this direction. Okay, so what beta decay does is change the number of neutrons by 1 to a proton. And so beta decay changes our element, whereas neutron capture just allows us to build bigger and bigger isotopes. So what happens here is we have neutron capture, makes something which is unstable. That unstable thing decays to form cadmium in this case, cadmium 110. This is actually stable. Now this process can continue. As long as you've got a source of neutrons, this process can keep continuing. And so we have a schematic which looks something like this. So cadmium actually has lots of stable isotopes, so you can get quite a long way before you become radioactive and have to decay again. But in this way, just by bombarding material with neutrons, you're able to build up successive elements. I'm going to forget something now. So we have silver, cadmium, indium, tin. I gave this talk last night and I blanked on what SB was again. Antimony? No? Antimony. That seems right, so maybe I've got it right here. But in this way, just by having lots of neutrons and then having these beta decays when you become radioactive, you can transmute silver to form all of these other elements. Now, this is just a portion of what's happening here. This process extends a lot in this direction and down in this direction. And so if we add in this process for the stars that we've already considered, the exploding white dwarfs, the low mass stars and the high mass stars, this is what happens now. We start populating this lower end of the periodic table, these bottom end over here, where we contain all the heavy elements. And we've made some progress. But crucially, for my telescope, for the Webb Telescope, we haven't made very much gold yet, just a little bit. Right? If this was the only process, gold would be even more expensive because it would be even rarer. So roughly a factor of 10 times rarer than it actually is. But we can also see there are other gaps as well. So first of all, there is this gap over here. We're missing the beryllium and the boron. These are two relatively light elements, so why haven't they been formed yet? And crucially, we're missing this gap over here. Now, I'm not going to dwell on these two very much, other than to say it's a relatively boring process. What happens here is that if you hit a carbon-12 hard enough with a proton, you will knock off another proton, and it becomes boron-11. So this is something called cosmic ray spallation. And it doesn't happen in stars, it happens all around the galaxy. Okay, so cosmic rays are very, very energetic particles. Every now and then they will hit a carbon-12 and they will turn it into boron-11. And if you then hit the boron-11, you can turn that into the beryllium as well, if you do a few successive hits. And it turns out once you actually properly account for this, you are able to explain the boron and then the beryllium, and also the relative abundances. So that's cosmic ray spallation. So we're getting there, but we still have this bottom part over here to explain. So it turns out when very massive stars die, they don't necessarily get completely destroyed. In analogy to the white dwarfs, you can actually form a different type of object called a neutron star. Okay? A neutron star is an object which is incredibly dense. It has a size, a physical size, of only about 10 kilometers. So about the same size as the city of Brighton, obviously where I'm from. But you have the entire mass of a star in that very, very small, confined volume. That's incredibly, incredibly dense. This is almost entirely composed of neutrons, but it does have some heavy elements in there as well. So the moniker neutron star is actually a little bit misleading because they are more complicated than this. They're essentially the leftovers of when very big stars die. So when very big stars die in these supernova explosions, they will often leave a neutron star. Okay? But they actually can be completely destroyed, or they can actually form a black hole as well. but in many cases they leave a neutron star. The neutron stars are actually also the origin of pulsars. So these are very rapidly spinning neutron stars, which we detected in the 1960s via radio waves. Now, occasionally, this is incredibly rare, but occasionally pairs of neutron stars can interact with each other and actually spiral into each other and collide. Now, for a long time, we've predicted that this is the case. But the problem being that when these collisions happen, you produce an explosion, but you don't produce very much light. That, combined with the fact they're very rare in the universe, means they were very, very difficult to actually find. This all changed, though, 3 years ago in 2016. Okay? The reason why this changed was we had the construction or the refinement of a gravitational wave observatory. This is a project called LIGO and Virgo. This is actually 3 different observatories spread across the world. Now, this observatory doesn't observe the universe in light anymore. It doesn't observe the universe in the same way that we can see the universe. It actually detects something called gravitational waves. Now, gravitational waves are a prediction of Einstein's general theory of relativity, so they're now 100 years old. Gravitational waves are produced whenever anything with mass actually moves and accelerates. So as I walk across this room now, I'm accelerating because I'm changing direction. I'm actually producing gravitational waves. But it just so happens my mass is relatively low, certainly compared to a neutron star, and the gravitational waves that I produce are really, really tiny. They would never be picked up. Neutron stars are different, though. They're incredibly dense, okay? They're incredibly massive, but crucially, they can get very close together just before they merge, and when that happens, they're accelerating really, really quickly, and this produces a huge amount of gravitational waves. Now, 3 years ago, the LIGO and Virgo experiment detected the first gravitational waves. Those first gravitational waves are actually detected when 2 black holes, which are even more extreme, merge together. But what happened 2 years ago now, in 2017, is this experiment actually detected something a little bit weaker. Not 2 black holes, which are generally more massive, but 2 lower mass objects. And this triggered lots of excitement because they knew roughly on the sky where this event was happening. And so what happened very rapidly is that many of the largest telescopes in the world all pointed at one particular area of the sky where this signal was coming from. And what they found was amazing. What they found was, in this galaxy, we see this little bright spot of light. This spot of light is this explosion. In this case, you can see that that explosion isn't particularly bright compared to the rest of the galaxy. This explosion over here is 2 neutron stars merging together. We know it's 2 neutron stars merging together because if you look at how this light changes over time and the wavelength of this light, you can work out what's actually causing that light. And it turns out what's causing that light is the formation of heavy elements. What you're actually seeing here in this light is the in situ formation of heavy elements. Okay? So this explosion was detected in visible light over here, but also by other observatories as well. And by looking very closely at this light, we could confirm that this was a neutron star merger, which agreed perfectly with what the LIGO experiment found. And if we look very closely at the light, we see that it's driven by the formation of heavy elements. Now, when you combine what we see with theoretical modeling, and you try and see what the contribution was, we see this. We've explained the periodic table. So there are gaps here, but remember these are the radioactive things, which are very transitory. They don't survive very long. We've now filled in the gaps to the periodic table. So with the confirmation that this final process actually happens just 2 years ago now, we have now explained the origin of all the elements. Now that's actually overstating things a little bit, right? We don't think there's anything massively crucial missing now, but there are lots of details to work out. For example, in all the modeling that goes into making this diagram over here, we need to assume that some fraction of stars live in binaries. There's lots of uncertainties that go into here. But it looks like we can certainly get the right answer by including all of these processes now. It doesn't look like we need another process. So fantastic. Astronomers have maybe for the first time ever actually converged in actually explaining one thing. Anybody who's familiar with astronomy might know that it seems to be some kind of cosmic joke that whenever astronomers look further into the universe, look more closely at something, something entirely new pops out and tells us that the universe is wrong. So this is actually what drove Einstein. So Einstein's general theory of relativity, one of the motivations for it was that when people looked at the orbit of Mercury, it wasn't behaving like it should do according to Newton's gravity. And this was one of the reasons why Einstein developed his general theory of relativity. Now, as we've looked closely at the universe, we realize that there is lots of things missing. And so it turns out, while we've explained the origin of the elements, it turns out the elements that I've just talked about, the normal matter in the universe, actually are only predicted to make up around 5% of all of the energy in our universe, with the remainder made up of dark matter and dark energy. These are effectively terms of ignorance. They're called dark because partly they don't interact with light, okay? But partly because we don't know what they are yet, okay? So it's kind of sobering that although we've solved one mystery maybe, working out the origin of the elements, there is this actually much bigger, deeper mystery which has been revealed to us over the last few decades. We now think there's something which acts like matter but doesn't interact with light, so it has a gravitational effect. But we also think there's something else which actually dominates over this, which has an even weirder effect. It appears to push galaxies apart on very large length scales. Now, we have ideas for what these things could be. This could be a new particle that we haven't yet discovered, but it could also be a whole load of little black holes. Dark energy is more elusive, and we do have ideas for what this is, but there's zero consensus at the moment. But there are many, many experiments now designed to test this. So that brings me to the end, and so I'll just state some conclusions over here. The atoms that make up your body were mostly produced when a very massive star exploded hundreds of millions, if not billions of years ago. Right? You are literally the stuff of stars. The atoms in your body, you only exist because stars died in the past. But even cooler, I think, the precious metal in your jewelry, which many of you will be wearing, was all created in an even rarer event, probably even longer ago, when two neutron stars, themselves the leftover remains of massive stars, managed to get together and collide and form something new. So there's kind of a nice poetry in there, how jewelry, which is often used as a symbol of love or partnership between two people, actually has its origin, the elements that make it up, has its origin in these two neutron stars coming together to form something new. This is my little joke for anybody who is a Tolkien fan, that arguably gold or your rings being forged in these neutron star collisions is actually even more impressive than the fires of Mount Doom. But the cautionary note is that although it looks like we've maybe got most of the way to solving one problem, astronomers have found this other deeper problem now, that virtually 95% of the universe is in a form that we don't really understand yet. We don't have a good explanation for yet. And this is why astronomy is such a big field still, because the hope is that by understanding this dark matter and dark energy, we learn more about the actual universe itself. And that might have amazing implications for technology down the line, who knows. And just as a final advert, because it is very close to my heart, the Webb Telescope, which is currently under construction and has been so for the last 25 years, will hopefully be launching in 2021. And again, I caveat this with maybe, because I've been caught out by this before. And I will end there and ask if there's any questions.